Okay, so the next lesson here is on connectivity. Now, I should say that connectivity in graphs is a very important subject. It's a rich subject. Uh, Connectivity in networks, I mean, that's a thing that people care about in the real world, and this is a place where graph theory has a great deal to say. We will be coming back later in the course and doing a whole unit talking about connectivity. Our goal today is not to try to jump in and deal with this great subject, but just to get a first definition or two in place so that we have some basic concepts that will be vital for us in just helping to get a picture and work with graphs. And we're going to sort of continue to be a little bit slow and careful in putting the pieces in place and being precise about what we're doing here. Right, and so let's get rolling. So connectivity. Now, our first definition here. I don't know why my coming up. So our first definition here is it's a little bit of a subtle one, and this is a thing that catches people off guard and people get wrong. So I really want you to take some time and think this one through. So we're going to define what's called a walk. So a walk, say W, in a graph G, is a sequence. So it's going to be a sequence that looks like V0, E1, V1, on up to En and Vn. And those E's and V's, those are edges and vertices. So this walk, it's going to start with a vertex, then edge, then vertex, then edge, then vertex, then edge, then vertex, then edge, ending at a vertex. Now the rule in order to be a walk is that for every edge EI, its ends are going to be the vertices on either side, which would be VI minus 1 and VI. Okay, so again, so this is a concept that has a graph, that is a thing on a graph, right? So I know this may look a little bit like path, and we've said path before, and I'll come back to the differences here. But again, a walk is a thing it's kind of on a graph. So I give you a graph, and a walk W in that graph is going to be a sequence of vertices and edges. So it's alternating vertex, edge from that graph. And the rule, again, is that every time you see an edge, its two ends have to be on either side. So let's, just in the hopes of keeping things as clear as we can, let's do a little example. Okay, so here's a graph. Oh, how about I do? Okay, so there's a graph with some vertices and edges, and let me tell you a walk. So here's a walk. I'll call it the walk W. This is going to be a sequence. Let's say it starts at vertex. Maybe it'll start at vertex 3 and then go along edge C to the vertex 4 and then along edge D to the vertex 5. It can go along H back to 3 and then along B to 2 and then along A to 1. So that's a perfectly good walk. So again, the walk W is a sequence. It's just a sequence that alternates vertex, edge, vertex, edge, vertex, edge. And again, the rule is that anytime you see an edge, its two ends are the two vertices you see on either side. You are allowed to have a loop in a walk. It just means that you walk from that vertex back to itself. So I could as well modify this and let's add a loop edge here. That'll be the edge I. I could then, I got to vertex A, right? Or sorry, vertex 1, right? So I could go 1 and then I and then 1. And okay, I may make a mess of things, but I could try to draw this walk on the graph. I think I will make a mess of things, but hopefully if you're following along, it'll be okay. So this walk starts at the vertex 3. It goes along the edge C to 4, along the edge D to 5, along H back to 3, along B to 2, along A to 1, and then around I, and then it ends. No, that wasn't the worst. Okay. Let me add a couple more bits of terminology here. The walk is, so this walk, oh, shot my size down again. Okay, so this walk I've described here is, we say that it is from V0 to Vn. So the first vertex is the starting point, that's where it's from. The second one it goes to. And it has length n. Again, the length here is the number of edges that you're transversing. We're thinking about sitting on a vertex of graph and walking along an edge to another vertex. If V0 equals Vn, then we say that this walk is closed. Okay. Now for the thing that everybody finds a little bit confusing, and I'm just giving it to you straight. This is how graph theorists operate. This is what we do. We allow a little ambiguity in some of the notation. What you're going to recognize here is that walk and path look very similar, right? And I want to speak to the differences first, so that we're totally clear. So you remember, I think just in the previous lecture, we defined what a path was. A path is a graph, and that graph has a set of, say, n vertices and n minus 1 edges with a certain incidence pattern, right? And it just kind of goes like this. A walk is very similar, but it is a different thing, because a walk it's not a graph. A walk is just a sequence of vertices and edges. Now, the walk has the same rule as path in the sense that it's a sequence, vertex, edge, vertex, edge, vertex, edge. And every time you see an edge in that sequence, the two vertices you see on either side will be its ends. However, they are formally different objects, right? So a path, as we've defined it, is a kind of graph, and a walk is not. Now, there are other things that are happening here. Walks also are allowed to repeat vertices. Right, so you're allowed to go on the same vertex and edge over and over and over again. If you want, you can have a 2-vertex graph, x and y, and with just one edge, e, and you can make a path that just goes x, e, y, ex, ey, ex, ey, ex, ey, ex, ey. That's a perfectly good path. Sorry, that's a perfectly good walk. That's a perfectly good walk in our graph. So a walk, it's just a vertex edge sequence where we imagine you're standing on a vertex, you traverse an incident edge to another vertex, and then you carry on. Now for the abuse of notation. In the case when you have a walk and there are no repeated vertices, then we will also allow you to call this a path. If you have a walk with no repeated vertices, if you never repeat a vertex, then you have a vertex edge sequence that looks just like a path. That set of vertices and edges form a path in the graph, and we're also going to call this walk a path. If V0 up to Vn are distinct, we also call this walk a path. Now, let me say, this is a little bit of a bummer. This is a thing you might find a little bit of an annoyance at the beginning, and I think it maybe it's a cause of some confusion. This really is how the grown-up graph theorists operate. What's going on here is that now when we are using the term path in a technical sense, we could mean two different things. We could either mean a subgraph of your graph G, like a path in G can be a subgraph of the graph, so a collection of vertices and a collection of edges and an incidence relation, or it could be this vertex edge sequence where you never repeat a vertex. And at the end of the day, they both come from exactly the same structure. Like if I draw a graph and indicate a little path in it, that path you could interpret either as a walk, this vertex edge sequence, or as a subgraph. And the truth is, so morally, these two things are essentially the same. And so in a greater sense, this doesn't tend to cause too much confusion, but it is worth keeping track of when you're going to manipulate these objects formally, when you're going to write down your proof. Are you talking about a walk, or are you talking about a subgraph? Like if I give you a path, it should be clear from context whether or not I'm talking about a walk or whether or not I'm talking about a subgraph. Okay, so that is that's the notion of a walk. So really, I think maybe the best way of thinking about this is at least for the moment, kind of trying to separate ourselves from thinking about subgraphs, right? So in the last unit, we introduced graphs. You can have a subgraph of that. You take some stuff away, and now you have a subgraph. A walk is really a thing that's on the original graph. So I draw the graph. Here's what the walk does. You just move around the graph. Okay, good. So let's step forward with our first big definition, and that's of connectedness. So a graph G is connected if for every pair of vertices there's a walk from U to V. So for all U and V in V of G, there is a walk from U to V. A graph that's not connected is going to be called disconnected. I think I will save myself the digital ink here, but that one appears in the notes. Let me point out one very trivial thing that comes with our definition of a walk. Every vertex has a walk from itself to itself of length 0. So you are allowed to make a walk that just starts at your vertex and ends at your vertex and has no edges. Remember, I said you have to alternate vertex edge, and start and end at a vertex, but they're allowed to be just the same. So there is a trivial walk of length 0 starting and ending at any given vertex in the graph. So you can always get from a vertex to itself. An interesting question is, well, what other vertices can you reach? And this is not a very complicated thing, but I want to do this carefully and slowly so that we get all these pieces in place the right way, and we can build on this. So we're going to prove a couple of easy propositions about this this concept of connectivity here. So our first proposition is the following. So if there's a walk from U to V, then there's a path from U to V. Okay, so if in some graph you can walk from U to V, then you can find such a walk that has no repeated vertices. And this sounds right. I think this is a thing that everybody can kind of tell, but it probably is worth a little moment here to stop and think about how we might prove it, and how we might prove it in a nice way. So, we we're now assuming that we have these two vertices u and v in our graph, and there's some way of walking from u over to v. Now I'm arguing that you can do that without repeating vertices. Now, one way you could imagine trying to prove this would be to take some walk, right? You know what I've given you here is I've given you the presence of a walk. So I've told you there's a walk from u to v. You can choose one, and then you can imagine trying to kind of modify it iteratively, like trying to shorten it up. And that's effectively what we're going to do. But there's a nice way of kind of cutting through this even quicker and just wording the proof as very, very cleanly. And let me show you how that works. So the idea here is we know again that in our graph there exists a walk from u to v. So there's some walk, vertex edge, that starts at u and ends at v. That's what we've been given. That's the only thing we've been told about our graph. So that's clearly what we have to use. So we're going to be taking advantage of that. Now, one thing you could do is you could just take any old walk and try to make it better, but you could also make a clever choice. Here's another thing we could do. We could choose a walk from u to v of minimum length. Right? So if you imagine walking from u to v and you imagine you revisit some place that you that you went before, you could probably see how you could shorten that. Right? So one thing you could do is kind of write this argument in a way where you take a walk and then you from u to v and you keep shortening it. But there's a way of writing this that I think is even cleaner. And what we're going to do is we're just, instead of making an arbitrary choice of walk from u to v, we're going to choose a shortest one. So let's choose a walk from u to v. Whoa. Of minimum length. Let's suppose that's, so I'll take my walk as v0, e1, v1, e2, v2 on to v sub n. But here, so u is going to equal v0. Oop. So let me just sort of write in a different color here. So v0 is equal to u here, and vn is going to equal v. So I'm choosing a walk of minimum length from u to v. Now, if this walk is a path, if there are no repeated vertices, then we're done. Right? Then I've already found my path. So that's all I'm trying to prove. I'm trying to prove that these vertices are all distinct. So what I'm going to do now is I'm going to suppose for a contradiction that there are two vertices in this sequence that are actually the same vertex. Suppose that vi is equal to vj for some valid range of these vertices. So I should be I has to be at least 0 and smaller than j, and j has to be at most n here. All right, so let's suppose that you did repeat a vertex. Now, so I've given you this walk that goes from u to v. You start at u, which we're also calling v0, and you just walk v0, e1, v1, e2, v2, so on. Eventually you get to the last vertex v, which is also v sub n for us. Now we chose our walk to be the shortest walk from u to v. I'm now supposing for a contradiction that you see the same vertex appearing twice in the walk. So some vertex appears here and then it appears again here. Now, if that's happening, you can see a natural way to shorten this walk, right? If you walked You walk to this vertex, and then you walk around and come back to it, and then get going on your way. We'll just cut out that middle part where you went from that vertex back to itself. So now, if I just walk up to v sub I, so I walk up to that vertex v sub I, but v sub I equals v sub j, right? So I can now, v sub I is equal to v sub j, so I can now just keep walking as though I were at v sub j. So I'm going to walk next along ej plus 1 to v sub j plus 1 on up to vn. And now what I've produced is a shorter walk from u to v. Now, I don't have any more room to write on this page. It's hard for me to write verbose proofs, as you can see. Now, what's happening is, well, I can switch into typing mode and when necessary, but here I'm just going to work with this. So what has happened in this argument? I'm assuming there's some walk from u to v, and I'm trying to prove that you can find such a walk that is a path where you don't repeat vertices. Now, what we have done is we have chosen, instead of just choosing any old walk from u to v, we've chosen a shortest one. That's a thing you can always do. I've told you there are walks from u to v, let's choose a shortest one. That's a nice thing to do. So when we choose a shortest one, that shortest one has some additional features that we can take advantage of. So this shortest walk from u to v, basically I'm claiming here that that is in fact going to be a path, and that's what we're proving here. So if you suppose for a contradiction that there is a repeated vertex, then you can, so then what this looks like is you start at your initial vertex, walk to this vertex, and then you walk around and then come back to it, and then you keep going to where you're going. Well, no problem, just cut out that middle step where you walk from a vertex back to itself. And if you just cut that part out, you're going to be left with a walk from u to v, which is shorter than your original walk. And that contradicts our choice. That's a contradiction, right? We assumed that we had the shortest walk from u to v. We have now constructed an even shorter walk from u to v. That's a contradiction. That can't happen. And that means that, that wasn't the case. So we did not have vi equal vj for some I less than j. And that means that our walk was, in fact, a path. And that completes our proof, right? So this is not deep math here, but it's worth paying attention to the manner in which we are proving things. We are told that there's a walk from u to v. We are trying to show that there's a path from u to v. The thing we have done is, instead of taking any old walk, we are choosing a shortest one, and we're taking advantage of that. Good. Okay, so let's do one more easy proposition. So this is another very natural one. A graph G is disconnected if and only if there's a partition of the vertices into two sets so that no edge has an end in one and in the other. So G is disconnected if and only if there is a partition say x, y of the vertex set of G such that no edge has one end in x and one in y. Let me just note that this is just convention in mathematics. When I say partition of a set, so when you have a partition of a set, it's a collection of disjoint subsets whose union is the whole set, but those sets have to be non-empty. So in this case, x and y both have to be non-empty sets. So you're not allowed to take one of them being empty. Now, we have an if and only if statement here. So, but the if part is pretty easy. So I'm going to actually say the if part is immediate. But this is in part because I don't actually want to write too much. Why is the if part so easy? Suppose you have this partition of your vertex set into x and y, and I promise you there are no edges with one end in x and one end in y. Well, then you can't, if I pick a vertex in x, say little x, and a vertex in y, say little y, it's not possible to have a walk from x, that little x, to little y, because your walk is never going to be able to take an edge that starts in x and ends anywhere but x, right? You can never go from x to y because there are no such edges. So that direction is quite easy. Let's do the only if. So for the only if, let's start from what we have. So I have told you that the graph is disconnected. By our definition, that means there are two vertices with the feature that there's no walk from one to the other. So I can choose two such vertices. So let's choose x and y vertices such that there's no walk from x to y. Right? That's what I'm allowed to do. I told you the graph was disconnected. What it means to be connected is for every pair of vertices, there's a walk from one to the other. If you're disconnected, then you fail to have that property. So that means there must exist two vertices, say x and y, so that there's no walk from x to y. Now, here's what we're going to do. I'm going to take these two vertices and define a pair of sets. Actually, I'm just going to I'll take these two vertices and define two sets. I'm going to define x. This is going to be a subset of vertices. This is all of the vertices so that there exists a walk from little x to that vertex. So x is going to be the set of all vertices, say z, such that an x to z walk exists, and I'm going to declare y to be the complement, all the vertices not in x. Now, let's say a couple things that we know about these sets x and y. First off, little x is in the set big X. Why is that? Well, I know that there's a walk from any vertex to itself. So my set capital X, this is the set of all vertices that can be reached from a walk starting at our vertex little x. I know you can walk little x to little x, so that means little x is going to be in that set. On the other hand, I know that the vertex y is not going to be in that set, right? By assumption, there is no walk from x to y. So x is in x, y is in y. Things are lining up just the just the way you'd hope. Now what I claim is that there's no edge from x to y. Let me just draw a picture up here. So here's our set capital X, and it's got this vertex in it, little x. Here's our set capital Y, and it's got this vertex in it, little y. And I'm claiming that you do not have an edge from that set capital X to that set capital Y. And I'm not sure I'm gonna so the claim here is no edge has an end in X and an end in Y. And if we can prove that, then that's certainly going to complete the proof. But let's check why that's true. So I'm as usual, you will find a slightly more verbose and complete write-up of this proof in the notes. I'm really right now, I'm just trying to indicate why this is true. Why is it the case that you do not have some edge that has one end in X and one end in Y? Why couldn't you have an edge, say, that goes from this vertex U in X to this vertex V in Y? Well, let's think. If that edge was present, what does that mean? Well, the vertex U lies in the set X. So by the definition of the set X, that means there's a walk from our vertex X to that vertex U. Well, if there's a walk from X to U, and you have some edge, let's call it E, that brings you from U over to this vertex V, where V is in Y, if you gave me a walk from X to U, I can append the edge E in the vertex V and suddenly get over to a vertex in Y, but that's not possible, right? By assumption, no vertex in Y can be reached if you start a walk from X. So what that means is this edge could not possibly exist. If you gave me this edge, then I just get a contradiction. Again, by assumption here, by our setup, X, capital X is all the vertices you can reach starting at little x. Y is all the vertices that you cannot reach. If you were to imagine an edge from this capital X to capital Y, that would immediately give us a contradiction, because that would mean that you could start a walk at your vertex little x and get to one end of this edge, and then traverse it and then get to the set Y, but that's contradicting our definitions. Y is the set of all vertices that cannot be reached starting a walk from X. So that's a contradiction. That means there are no edges between X and Y. And what that means is that we've found the desired partition, and that is indeed completing the proof. Okay, so I'll stop this lesson there.